okay, it might be useful to look over the last few years of physics exams just to kind of go through. I mean, first of all, the choice is incredible. I think they're all falling over themselves in different subjects to give the most generous choice possible. When in the old days it was kind of, they were being stingy about it. Now the quest is to give as ridiculous choice as possible. I mean, if this continues on, some year it'll be just, here's 20 questions, answer none of your choice. But at this point we have two questions from section A, from last year anyway, and I think 2020 is going to be similar. So two questions from that section for the experiment, and they're usually fairly nice and accessible. All of those, the experiment ones, are going to be on really right on the diagram. So doing a proper diagram, nice big, well constructed diagram is crucial to those, because everything then flows from that diagram. Then we'll have a look at those later. And then section B, we have 4 questions out of, I think, 9, which is a pretty generous choice. And then even within those, you have choices within choices. So, and I think one of the nicest questions is this question 6, which is one that you should almost definitely do, I think. So 8 parts out of 10. And I'm not normally one for encouraging too much of doing extra questions, because I think there's an opportunity cost there. If you do extra questions, the opportunity cost is you're losing out on reviewing what you've already done and perfecting it. But if you can do both, then that's fine. And I think with these micro questions here, which are 10 of them, and you do 8, I'd suggest you do your 8, and you definitely try and attempt the other two. You've nothing to lose. And I think usually the format, if you're doing mostly mechanics and a bit of electricity and maybe leaving out a lot of other areas, then you'll find you almost always have 8 questions here. You might be squeezed on the 8th one, but then even the ones that you haven't really covered, they're fairly basic sometimes. For instance, maybe if you haven't done heat, 2 different types of thermometer give different readings placed in the same environment. That's just about the measurement process and about the error that's associated with every measuring device. And it's a fairly fundamental thing rather than just being specifically to do with heat. So it suggests definitely doing your rock solid 8 and attempt the other 2. You've nothing to lose, and because they're so short, you're not sacrificing a lot of time. Then the other question at the end is question 14, which where you do 2 out of 4, and I think that's quite a good question as well. So it's almost always a mechanics type question. So simple harmonic motion there in A, hydroacoustics, Doppler effect tends to be very popular. So those 2 would be 2 quite good questions there. But then the other 2, there's always going to be at least one that you mightn't have done. Photoelectric effect, ball lenses, that should be fine. That's critical angle. So you have 3 out of 4 there, and then you have to do 2 more out of the rest, and there's usually one nice mechanics one, and then this is light here as well, so that should be okay. That should be fine. So yeah, so that's the format. So this one I think is a lovely question, section B, section 6. But let's just go back and have a look at the experiments first, the experimental side of it. So I think you have 5 here. 4, yes, 5, which is an incredibly good choice. So there should always be enough here to do 2 decent ones. So experiment, so there's 2 types of G experiments to find G. There's the pendulum one, which is this one, and then there's the free fall G. So last year they asked the pendulum one, maybe the free fall one this year, or else maybe principle of conservation of momentum for 2022, but they're all pretty much the same fundamental thing. So simple pendulum set to oscillate, and the procedure repeated. Label diagrams, okay, so very important that label diagram, that is very clear. And what I'd say is exaggerate the size of crucial items. So don't the ball at the end of it, don't put it in terms of, don't put a tiny ball, put a reasonably good sized ball, because you'll have to indicate the center of that ball, which might be useful at the end of questions. And that's just it. So if it's tiny, that will not be clear. So do it nice and big, any of the crucial elements of it. Okay, the fixed point is suspension and the distance L. So why did the students do it for 20 oscillations rather than one oscillation? Well, that's a fundamental question that'll be asked all the time, and it's the principle of experimentation. The more times you measure things, then the error gets kind of averaged out. So if you do just one oscillation, there might be an error associated with it. If you do 20, then some of them will be errors associated with them, but the more you do, the more times you perform an experiment, the more accurate it will be on average. Okay, use the data, and you get an average there for that one. So use the data to draw a suitable graph. So then at that point, what you have to do is find the equation in the log tables for the relationship between the swing of the pendulum and G, in terms of L, T and G, and then so determine G. So by doing that, you'll have to draw a suitable graph. So you'll have to manipulate this and convert it into a usable form depending on the equation that you find in the log tables. So redo the table in terms of the new variables that you need. Sometimes you have to square quantities. I can't remember what it is in this case now, but what is it, square root of L over G or something like that. So you might have to get the square root of one of them, I think. Yeah, square root of L over G or something, or 2 pi square root of L over G or something like that. So you might have to get the square root of this versus, or it might be L versus T squared, might be an easier way of doing it. Can't remember exactly the formula. But so that will almost always have to be converted. Now you may have to go standard with the units, but not always. So don't worry about that too much, as long as you can remember at the end that when you go into the equation, it'll have to be standardized. So you could plot it in millimeters, or it might be millimeters squared in this case, but just remember your conversion later to meters when you're using the equation, as long as you make sure of that. Otherwise G will come out, it'll probably, instead of 10, it'll come out at 1,000, or it'll come out at 0.001 or something. You'll know you've made a mistake in the units, or the units at that point, but don't wait till then. Okay, so that's your typical thing. They almost always ask about something to do with experimental error. Focal length of a concave mirror. Yeah, this is a nice one as well. So your equation, which is in the log tables again, is 1 over F is equal to 1 over U plus 1 over V. So again, you'll have to draw a new table, or else, well, are you going to plot it with just 2 points? Probably not. But yeah, a new table with your UV, and then convert them into 1 over U, 1 over V. Why did the student make a measurement of the focal length? Well, that's important because you need to know where the focal length is when you're putting your object in front of the concave mirror. You need to know where the focal length is and keep it well outside the focal length. So that, because if it's inside the focal length, you might get a virtual image. As far as I know, you get a virtual image, yeah, behind the concave mirror if it's inside the focal length. So you want to keep it well outside, or maybe more than twice outside the focal length, in order to get a real image. How do the students determine the image positions? Well, you probably have, depending on how you did the experiment, but you're probably using a meter stick, but don't just say just the meter stick. Say how you, what kind of object you use. So maybe it's a pin, and then the pin can't just float on its own. So it might be a stand, with a grip, and so on. And mention all of that. Don't just throw down a vague answer on it. Draw a label diagram. So that's important. Line diagram is important. On your diagram, indicate the U and the V. Use all of your, or you may be doing light boxes, of course. Yeah, forgot about that. You may have done it using light boxes. I don't know, depending on what you did. Calculate the focal length of the mirror. So you've got 2 data points, and you use your formula 1 over f is equal to 1 over u plus 1 over v. Get an average then of the answers. Now, and I suppose, yeah, 2 measurements is very low for experimental error. Experimental error there is going to be quite high. Another student was more wise. She measured it for 6 object distances. Drew a graph and use the graph method to sketch a suitable graph that might have been drawn. So you're going 1 over u against 1 over v. And how could it be used to calculate focal length? Well, it's a graph which will be that way. So y-axis, x-axis, and this will be it'll be a graph with slope -1, and it'll be so going that way. And where it cuts the y-axis, that'll be 1 over f, and when it cuts the x-axis, that'll be 1 over f as well, and you could get an average of the two. All right. Fundamental frequency of stretch string with tension. So that is that's a nice one as well. I think there's a square root in that one as well. So draw a label diagram how the apparatus is arranged. Describe how they use suitable graph relationship between f and t. So suitable graph means you're going to have to convert these into a form that's used. Find the equation first, and then, so let's try and find the equation. So for stretch string, yeah, light and sun probably 59. Okay, where is 59 there? Yeah, okay, coming to it. Yeah, here we are. Yeah, so fundamental frequency of a stretch string. So f is equal to 1 over 2l square root of t over mu. So mu is this mass per unit length of the string, t is the tension, and l is the length of the string. So where are we? Yeah, so write that equation down. Now draw a suitable graph. So what can we do? We have f and t there. So what's the equation? F and either square root of t. So you could draw f versus the square root of t, or you could do f squared versus t. And you'll just have different calculations at the end with the term, the slope. If you do f, sorry, let's see, hang on. So you have frequency and the tension. So you want to show the relationship between f and t. So do f versus t squared, and you should get a straight line. Use the graph to the mass per unit length of the string. So if you do f versus, say, the square root of t, then with f on the y-axis, x on the x-axis, then it'll be f over square root of t, so equals, so the slope will be equal to 1 over 2l mu. All right. So, and you know your string length, so that's a constant. So, and you can get your slope out of that. All right. Okay. So, let's have a look at some of the other experiments. 2019. Okay, acceleration due to gravity, free fall. That's a fairly popular one. Okay, so label diagram the apparatus. So again, you have to be very careful of that and make sure you use a ruler. You have to use a ruler to draw experimental diagrams. So you have your electromagnet, and again, make sure the ball is quite large so that you're not, because it's such a crucial part of it, really. And that will help you to answer questions later, like they say, you know, from where do you measure it? Well, it's got to be between the, so they ask you, I think, between which 2 points was the distance s measured. Well, because the ball is nice and big there, it'll be obvious that it has to be between the bottom of the ball and the top of the trapdoor. because it's the bottom of the ball that falls down, and the bottom of the ball hits this first. So that's when everything starts, and that's when everything stops. So that has to be the distance, S. So the electromagnet there, and then as you can see, you have a kind of a circuit. So with the timer here, once you press the switch, that releases the ball. A paper just between the electromagnet and the ball can help as well. There might be a question on that. So when you press the switch, the ball is released. And then the trapdoor then, once that's released as well, it kind of triggers this timer as well to make sure that it's at the end of it. So that is a pretty important one. So the diagram, just make sure they're clearly done. That can be done in just a minute, but you've no shortage of time anyway. So spend your time on the diagram, and everything else tends to flow. Nice big ball will make sure that your diagram, you don't lose marks later on when you're asked questions about what's happening, the dynamics of it. So describe how the time t was measured. Well, that's using the timer there and the switch and the trapdoor. Don't when you're answering scientific questions like that, make sure you're not loose with your language. Oh, they noted how long it took, this kind of thing. You have to be make sure you're always talking like a scientist. And that means you are clear. There could be no ambiguity. So you say, how time was measured. You're saying the switch was closed. This started the timer. The ball is released simultaneously with the switch being closed. The ball falls, hits the trapdoor, which cuts the circuit and makes the timer stop. And that measures the time. Okay? Don't use any loose terminology there. Draw a suitable graph. Okay, so your suitable graph, again, always you're looking for an equation. So in this case, it's S is equal to UT plus a half AT squared. And write down the full one first. You know it's starting at rest, so this bit can go to 0. So S is equal to half, and the acceleration is gt squared. So you can't just draw the graph from that. You need to always convert the table or into usable form. So S is fine, but then we need to, because the equation is in t squared, we need to plot S versus t squared. So you need to be squaring these guys. Always be aware of the units. So it's milliseconds squared now, or else you could convert it to seconds first and square that, so you get seconds squared. But just always keep track. Don't mix them up midway through. Commit one or the other. So then you draw your plot of S versus t squared, and you're going to get something like this. So remember, your line of best fit is to make sure that it's drawn where the points are scattered reasonably evenly about it. So that's like S over t squared, really rearranging that equation, is equal to g over 2. So that means the slope of that line is going to be g over 2. So if you double the slope, you'll get g. Okay, small dense ball, and they always ask these kind of questions. They had an advantage. So dense means it's not going to be it's not going to be carried by air resistance. So small and dense means it's not going to be carried by air resistance. So like if you had a large plastic ball there, air resistance might come in as a factor because it'll be carried by the air resistance and slowed down. A small dense ball will cut through the air much more efficiently, and air resistance will be negligible. All right, focal length of a concave mirror. I had a look at that earlier. How did she find the approximate focal length? So again, you take an object at infinity, and it's because of the way concave mirrors, and you'd be using a ruler for this, but so that's the pole of the mirror, that's F. So if an object is on infinity, then their parallel rays come in here and they end up at the focal point. So you find the approximation. So that's how you find your focal point. You take an object at infinity, and it'll be formed. The image of it will be formed at the focal point. Why do you find that? Well, because you get different images depending on where you place your object, and so you want to place the object well outside the focal length. If the object is within the focal length, it could be a virtual image, and you don't want that. So precautions should be taken when measuring V. Well, I suppose there'll be always measurement error. So if you're using a ruler stick, every measuring device has a certain amount of error associated with it. Make sure the item is in focus on the screen so that you're getting the exact position of the image. Okay, use all the data to calculate focal length. Well, 1 over f is equal to 1 over u plus 1 over v. Okay, latent heat diffusion of ice, and then current flow. So semiconductor diode, yeah, I mean they're fairly interesting ones as well because they're fairly basic. A semiconductor, so a metal obeys Ohm's law. So V versus I is a straight line because V is equal to Ri. So V versus I graph would have a slope of R. Not so with the semiconductor diodes. So you have V and I there. So an IV. So your voltage is increased, say, to 300 there. And what you find is it tends to be a graph like that. So as you can see, at low voltages you get almost no current through it, and then at a certain point the current starts to spike up. Draw a circuit diagram for the experiment. Use data to draw a graph of current versus potential difference. So I versus V. Determine the junction voltage. So the junction voltage is the point at which is that knee point at which the current starts to spike. So what happened when the diode, when the junction voltage was exceeded? Well, it basically acts like a nice conductor, and the current starts to spike and goes very high relative to what it was. It's only a trickle before the junction voltage, and then it spikes up. Is Ohm's law obeyed for this diode? Definitely not. Because for Ohm's law, for a normal metallic thing, you would have V versus I, and you would have that. So it's straight line through the origin, and the slope would be R, because V is equal to Ri. But for a semiconductor, you've basically got like 0 there, and then you've got a big spike. So it's a non-linear, because there's nothing linear about that. It's non-linear. It's almost like two-piece, where before the junction voltage you just got a trickle, and then afterwards you got a very big spike. So definitely doesn't follow Ohm's law. Diode is reversed, and the data is recorded. So state other 2 changes are made to the circuit for recording data over diode and reverse bias. So the circuit, when the diode is reversed, then you're in reverse bias, and you're going to get almost no current at all. So it'll go something like that. Because a diode is really designed to just let current flow in one direction, but there'll always be a little bit of a trickle of current that way. So your battery is turned around, or your source of power, so normally it will be there in forward bias with current flowing through here. So your battery will have to be switched around for that, and you have to anticipate a very low, but once it's switched around, then you have to anticipate a very low current flowing in it in reverse bias. Okay, so this is the nicest question on the paper, I would say, a section B, question 6 or question 5. I think it's now question 6 actually these years. But They're very short and snappy. You've about a half an hour for these questions, so I suppose with 10 you're talking 3 minutes each. Well, there's 8 strictly speaking, so probably 2.5 minutes each or something like that. So light year, calculate this distance. So a light year is distance traversed by light. A light year is a distance, so it's just something to be aware of that. Start with your basics. Speed is equal to distance over time. So distance is equal to speed by time. So the speed of any light is c, which is 3 by 10 to the power 10 to the power 9. It's in the log tables. So 3 by 10 to the power 9, and then in 1 year, calculate. So it's meters per second the speed is measured in, so you want to convert that to seconds. So 1 year in seconds, so it'll be 365 days by 24 hours by 60 minutes by 60 seconds. Yeah. Density of the apple, well, density is equal to mass over volume. You have a weight. Yeah, that's interesting. So it'll be okay, so the weight, so you have to get the mass from the weight. So you have the volume. So density is mass over volume. You have the volume there. So the weight is equal to mg. So to get the mass, you divide the weight by g. Book is decelerating and moves right. Draw a label and show the forces. Okay, that's an interesting one. And it's one of those ones where with applied maths it seems so simple, but just don't be complacent on it. And make sure that you include everything. So book is decelerating as it moves to the right. So we'll show that. Moving to the right on a horizontal table. Draw a label, show the force acting on the book as it moves on the table. It's decelerating. Okay, so, well, the first one, if it's moving to the right, then there's friction force is opposing that, and we'll call that F is equal to mu r. Everything has a mass and a weight, so always draw that in, mg, and then it has a reaction force r, and then F r is equal to mu r. So they are the forces on that. So really 3 forces, and the only force opposing that is the friction, and that's what's slowing down and decelerating the book. Polarization of light, so like shades, it's blocking light which is moving in one plane and allowing the other light moving in other planes in. Thermometric property of a mercury thermometer and a thermocouple. So you can never measure heat directly. You're measuring indirectly, and in these cases what you're measuring is the effect that heat has on something in order to measure it. So in a mercury thermometer, it's the height. Because the heat expands the mercury, then you hopefully have a linear relationship between the height of the mercury column and the temperature. And thermocouple, then it's your EMF that's generated in it. So sketch graph resistance and temperature for a metallic conductor. Well, resistance and temperature. So that should be reasonably straightforward. Power is generated resistor, yeah, P in terms of R and V, again straightforward, what should be fine. So start with your Ohm's law, V is equal to IR, but P is equal to V squared over R then. Polonium, so a lot of people might leave out those ones, and but I think the real one to focus on, even if you've left out this bit, is these questions, the activity of a sample, because it's pretty simple equations for these guys, and there's just 2 equations for it, so let's just have a look at those now. Yeah, and they're up here. So activity is equal to this. You're never really going to be encountering that. Law of radioactive decay, very simple equation. Activity is equal to lambda times m. N is the total number of nuclei, and then half-life is T half is equal to ln of 2 over lambda. So those are the only 2 equations you need. So A is equal to lambda n, and T half is equal to ln 2 over lambda. So looking at that guy, where is he? There. So calculate the activity of a sample that contains that many. So it has a half-life of 3 minutes. So we now know that. So T half. So just write down what we know. T half is equal to 3 mins, and I'd say we'll have to convert that to seconds to get it standard. Activity, yeah, we will. So 3 mins, so it's 3 by 60, which is 180 seconds, okay? And so we need A. So A is equal to lambda n. We know n because it says we have 75k nuclei. So that's n, the number. So we have this. So we just need this lambda. And that'll be easily got from this T half. So lambda, just rearranging this guy, is equal to ln2, natural log of 2, over T half. Get lambda, and then shove it into this guy, multiply it by n, and you get your activity. Activity then is in becquerel, so just that's the thing to remember, BQ. All right? Okay, so overall, I mean, those ones, I would say you have, if you look at what you would have there, without having done, say, nuclear, apart from that activity, well, let's have a look at it. So 1, 2, 3, 4, yeah, we'll come back to that. Say you might, well, you will have that, I'd say. 4, well, we won't count it for the moment. 5, 6, okay, so 6 good ones, decent ones. Those 3, 4, 5, 6. I would count that as a 7th with heat, and then you just need one more. And in that case, if you have that activity, just using that from the log tables, that gets you your 8. All right. So let's have a look at some of the other papers. Oh, well, have a look at the short questions at the end. So you have the micro questions, and then you have these ones here where you have 2 out of 4, which is a lovely one as well. Principle of conservation of energy, this is a lovely one. So mass at the end of the string given an initial velocity of 4, velocity of mass at position B, centripetal acceleration at position B. Now the trap not to fall into here is, don't assume that that's its maximum height. They quite often ask that if you give it a bump and then it goes to its maximum height up here or something. And they've even given the clue it's still moving at that point upwards. So it hasn't lost all of its kinetic energy there. So the velocity of mass at position B. Well, use your principle of conservation of energy, which you've just stated. So down here, it has no potential energy, but it's all kinetic. So half m4 squared. And up here then, it's got both. It's got half m v squared, we'll call it. So we're trying to find v, plus mgh. How would we find h? Well, we can get it from that triangle there. So we have a right angle triangle if we drop down here, and we can find that length there, which is cos 35. Yeah, because this string has a length of 80 centimeters or 0.8 meters. So it would be that length there to that point would be 0.8 cos 35. So then you can find out what that gap is, the extra potential energy that it's got, by putting that height into the mgh question, equate them, and you'll get your velocity. Centripetal acceleration then is equal to, what's the equation first? Mv squared. Well, your force is equal to mv squared over r. You have the mass, do you? Oh yeah, you don't need it because it's the acceleration, so it's v squared over r. So so just pop that in. That should be okay. Yeah, so this one, RAM, it's not really about RAM, it's more about capacitors. So what is a semiconductor? Well, it's the halfway house between a conductor and an insulator. So a conductor is like copper, so it will obey Ohm's law and it conducts electricity very well. Semiconductors only conduct electricity under certain circumstances. And what's meant by doping? Well, intrinsic semiconductor is when you just get your piece of silicon or your piece of germanium, and you use that directly and use the existing chemistry which has holes and electrons and use that. Doping is where the normal case whereby you help it along its way by you dope it using boron or something that has additional holes or electrons to basically improve the efficiency of the carrier of the electricity through it. So doping is something to improve the conduction of electricity through it, through the means of doping it with an impurity really that has either excess holes or excess electrons in order to convert it to an N-type or a P-type. So majority characters are electrons. Well, if you dope it with an N-type semiconductor, then that will have spare electrons. So if you dope it with that, then not surprisingly you'll have additional N types and electrons. So it'll become an N-type semiconductors. Majority character holds. So you're doping with a substance that has a lack of electrons, or putting it another way, it has an excess of holes, and that'll create a P-type semiconductor. Capacitance is 90 picofarads, operates a voltage. I like the capacitance questions here, and they tend to like them as well. They tend to be reasonably okay, so it's something to watch. Energy stored in capacitor when it's fully charged. Well, in the log tables, you have an equation which I hope I remember, which is E is equal to half CV squared. And I love the way that looks so similar to kinetic energy equal to half mv squared. And it's no accident because the fundamentals underneath these things correlate quite a bit. So where that's you have the capacitance there, pico, and it's F farads, yeah. So you have to go to the log tables to find out what little f means in terms of, it's not picofarads, it's Fs. So just make sure you know how to find those, because if you're converting with one that you're not familiar with, that you'll be able to find it. So it's instead of milli, or where are those? So your millis are mews, micros, and things like that you have, that you're able to get these. It's 10 to the power minus 12 or 10 to the power minus 15, those kind of things. So there's somewhere at the start. Can't remember where they are. Yeah, is that it? No, it is, I think. Yeah. So where's femto? So 10 to the power minus 15. Okay. So here we are. So centi, milli, you're all familiar with, so millimeters, micrometers 10 to the power minus 6, nano 10 to the power minus 9, pico 10 to the power minus 12, and femto 10 to the power minus 15. So that's a very small number. So that's 10 to the power minus 15 farads. So 90, so you have C, you have V. What's the energy stored? Well, it's half CV squared. Number of additional electrons in a negative plate for the result of it being fully charged. So then you have to go into your equation for your charge, and it's QV. Oh, I'll have to find it here. Where's your electricity? No, it's below that. Should have just gone from the thing. Heat and temperature, light and sound, electricity. Here we are. Okay, where is the capacitance? Capacitance is equal to Q over V. Q over V. So your Q is going to be equal to CV. C is equal to Q over V. So Q, the charge, is equal to CV. So your charge is equal to CV. Then go in to your log tables, find the charge of an electron. You get the total charge, find the charge on one electron, and then divide it so you get the additional number of electrons. Okay, and then this one was a particularly nice one as well. And it's a diver underneath and sees a circle of light. I mean, that is pretty cool. I didn't know that would happen, but it's due to the critical angle and refraction and total internal reflection underneath the water, which is pretty cool. So the critical angle, total internal reflection, is exceeded. So really you have water here, you have a diver down the end, and light is coming in at all angles and all this kind of thing, and it gets refracted, and so it gets refracted towards the normal when it's going into more dense material. But what you have in this case, so you have light coming in at an angle nearly 90 degrees to the normal. So when it's 90 degrees to the normal, it's coming in like that, and that's the critical angle. So that's the critical angle. And so in other words, if that was any bigger, then the light wouldn't be coming in at all. But it's at 90 degrees at that point, and that's the critical angle. So in other words, no more light comes in at that from that side, and the same with that. So basically all the light is coming in and just appearing as one dome of light here, and where that's just the normal. So that's the critical angle, which means by alternative angles, that's the critical angle as well, and that also. Okay, so the diver is, so total internal reflection. Okay, so how does total internal reflection happen? Well, if the critical angle is exceeded, okay, so you have, like that. So if you have something incident on a surface like that, then refraction will happen. If the incident angle gets bigger, then like that, then no refraction happens at all, and it goes reflected instead of being reflected back in. So you have total internal reflection rather than any refraction once the incident angle exceeds the critical angle. Okay, diver here is 12 meters below. When he looks up, he can see circular window of light. Calculate the area of that disk of light. Well, so you need to get the area of it. You need that radius there of that. You have the critical angle, do you? Well, critical angle, when he looks up, he sees, calculate this area, the risk of light. Why the diver is not appear to be at observer outside the refractive index of water. Yeah, you've given that. Refractive index of the water is 1.33. Is 1.33, and then you have a thing in the log table that says that's equal to 1 over sine C, I think. So that will give you the critical angle. Great. And then you just go sine C. Actually, you have sine C already, so you don't even need to convert it out into the angle. So sine C is equal to R over 12. So R then is equal to 12 times sine C. That'll give you R, then get a half pi R squared to get the area of that disk of light. Label dive does not appear to be at a depth of that when viewed by the observer outside. So you have the diver down here. So you have an observer somewhere here. Hooray! I like divers. So it'll go like this, and it'll be refracted away from the normal, remember? when it's coming out into a less tense. So it'll go into her eye like that. So she sees it. If you follow on that part there, the virtual image of the diver is there. Now that should be a straight line going from there to there. So because it's refracted and it changes angle, it goes like that. So you're tracing the line back on a straight line through the water, and so the diver appears to be at that point. So the apparent depth is a lot less than the actual depth. Okay, so that's the final question there, and that's usually a very good one to do, 2 out of 4. So I'd advise, if you can, try and do all 10 of the micro questions. Question 6, and this one, 2 out of 4. You might even sneak a third one if you're happy enough with your other 2 questions that you've done. Okay, so that 2019 paper is reasonably good, reasonably nice one. I would say it should be fairly accessible. And so magnetic field, photoelectric effect. Yeah, satellites, that's a pretty popular one to do. So really you've got the experimental question, loads of choice there. Be critical on the diagram, and the diagram decides everything. All the short questions where they're asking about experimental method can be explained if they're obvious from the diagram. Then this one, lovely question here. Try and do your 10 out of 10 if you can, even if you're just attempting. And then the final question, 2 out of 4 there is nice. Almost always get a mechanics-y type question then, and then hopefully one on light or sound or something like that, or electricity then afterwards, which you have, I think, a half an hour each to do. So hopefully that gives a better overview of 2019 paper and some of the others.